Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you. It's never happened. Christopher Bullhead's my friend. We're going to talk about Petoskey Stones today. Petoskey Stones are, if you're a Michigander, we probably have some Michiganders out there who are listening to this podcast. You know what a Petoskey Stone is. If you most likely, if you live in the state of Michigan, you know what a Petoskey Stone is. I think that's a pretty safe bet, or you've heard of it at least, right?
I would think so. It is our state stone. And I hate that. I hate that verbiage, stone. It's our state fossil, or it's whatever, but it's got to be something else, right?
Petoskey Stones are amazing. I've spent ever since growing up. I grew up going in the summers up to the northern parts of Lake Michigan, walking along the beaches where Petoskey Stones are really prevalent, and it is just like in me. When I'm walking along a beach, I'm looking down, no matter, even if I'm not on the shores of Lake Michigan, I'm looking for Petoskey Stones just because it's kind of this innate thing. They're a beautiful, beautiful fossil, beautiful, beautiful stone. That's the state stone of Michigan, and collectors love this. Yes. Casual, everyday beachgoers, it's a fun thing to do, to go look for Petoskey Stones. It's great.
It absolutely is fun to do. I have a ton of them, smaller pieces here and there and so on. Hey, Jesse, before we get into the geoscience of Petoskey Stones, we haven't done intros in a long time. So can we real quick just take a second?
Quick. We got to do it quickly.
We'll be quick. You are Dr. Jesse Rymink. You and I, we go away.
On the doctor. Emphasis on the doctor, Chris. You got to say Dr. Jesse Rymink.
Yes. I roll my eyes when I say it. But you and I go way back because you're one of my former high school students. You were in one of my high school science classes, one of my earth science class. And Jesse, after you left me, you eventually went on. I love that. You actually went on and got your PhD in Canada, and now you landed, I think, the dream job. To me, you are a professor of geoscience at Penn State University, which is one of the most esteemed geoscience programs in the country, in my opinion.
It's a pretty good gig, and I'll expect you to refer to me as. I think you should start calling me Professor Rymink throughout this podcast, actually. Okay, real quick, Chris Bullheis, as you said, my former high school teacher. You've been teaching high school at a really elite level. You've won national, regional teaching awards for earth science geology. You run a geology field course in the summer. You effectively teach AP geology, college level geology. You've built an astronomy course, and you and I have a deep passion for rocks, and we've gone collecting a lot together in Michigan and out of Michigan. We both grew up in the same area in Michigan, and so that kind of leads us nicely into Petoskey Stones, because Petoskey Stones are on the collector's bucket list, I think, especially in this part of the Midwest. If you're in the upper Great Lakes states, you're probably aware of Petoskey Stones. You've probably chased them down if you're at all interested in rocks. If you go to rock shops in Michigan, in Indiana, in Wisconsin, you're gonna find Petoskey Stones. It's guaranteed.
Unavoidable.
And actually, if you go to art shops, little artist shops,
absolutely.
There's often stuff made of Petoskey Stones in there too, right?
Yeah, that's right, because it's so pretty, and then it's a soft rock, and so it's easy to do things with, from a polishing perspective and jewelry making perspective.
That's a really good point, Chris, that we should definitely emphasize how soft it is, how you can polish this rock with just wet, dry sandpaper in your hands. You just rub it around your hands with some wet, dry, get the sandpaper wet and sand it down. You can actually polish this really, really beautifully. Chris, let's turn to image number one. Let's turn the images on here a minute and turn to image number one. This is a photo of what an unpolished Petoskey Stone looks like. This is just to kind of give you a sense of the scale of these things. So we got centimeters here in the units, and we're looking at the scale of the fossilized. This is a fossilized coral, and we're seeing this white outer rind with the inner kind of darker gray, darker sort of tannish gray, maybe even color. I don't know if that's appropriate, but this is what it looks like dry and not polished. So this is like the least interesting version of a Petoskey stone.
But
to
me, it's my favorite. It's my favorite.
Oh, is that right? Okay.
Flavor of the Petoskey stone. I love that. It forms this. When I look at that, I think honeycomb. It forms these kinds of like hexagonal sides to it, and so. Yeah, today we're going to get into why does Petoskey stone look like this? What were these organisms? What setting did they thrive in? Because that all ties back into the geologic story of the great state of Michigan.
It's a cool story. It ties in a whole bunch of different stuff here, from Devonian history of the region to this exposures today in Michigan. But the Petoskey stones are really they're found all along the shores, especially on the Lake Michigan side, so the western side of Michigan. They're found in the sort of gravel along the shores there, gravel and pebbles. They don't get huge, so you're not going to find a massive boulder of Petoskey.
Hold on, Jesse. Hold on. So there's a law apparently that you're not allowed to collect a sample that is more than 25 pounds. And a few years ago, this guy found a 90-pound chunk of Petoskey stone, and he posted it on Facebook. Yeah, posted it on Facebook, and the DNR came and took it.
Oh my goodness, really?
Yeah.
DNR is Department of Natural Resources in Michigan. Okay, so this caught enough online traction that they came and took it from him. That's very funny. So I'm aware of this rule, Chris. It's designed for rock collectors, basically, on the beaches, because you can take some samples, like check your local areas, because some of these areas are in national seashore, and it's a completely different ballgame there. But in many areas you can collect little pieces, but you can't collect more than 25 pounds per person per year. So obviously 90 pounds exceeds that by quite a lot. So that's a really funny story.
And the person did not intend to break the law at all. This was just he was proud as can be, like, hey everyone, look at what I found.
Look at how big I found this
took
thing.
A little bit of heat for it. So
I think, Chris, we should mention that these things are often kind of small, and here's another photo of these things stacked on Petoskey stones stacked on top of one another. They have a lot of different different color characteristics to them, but this same hexagonal pattern. You'll often find them this size. Like if the rock is totally Petoskey, this fossil, they'll usually be this size. If you start getting bigger, you'll have one corner that is fossil. You won't have the whole rock that's often fossilized. It's really rare to find a monster one, and that is because of the history of these rocks. These are fossilized coral and colonial corals, and so those colonies did not grow to the size of house-sized boulders. Often they're kind of smaller colonies that then became fossilized. So that's kind of the story behind just the sizes that you find here. But Chris, paint us a picture. Like every rock tells a story. What's the story that these rocks tell us about the ancient planet?
So you talking about like the paleo setting? Is that what you're asking about?
What were these forming in? Like, set the scene for us.
Yeah, so I think that's a good place to start. So
we're talking about 5 years old at this time or something?
Yeah, I knew that was coming. Yes, yeah, I was 370 million years old at the time. So yeah, this was in the Middle Devonian, and so this is in the time frame of 375 to 360 million years ago. And the region that is now northern Michigan, and I'm going to do this. Jesse, is this right here like this? Is that?
It's right.
Is this?
Yes.
Is it
exactly
correct?
Right.
Okay.
Yep,
all right.
It's correct from my view.
We're talking about like up in this area, right up in here. This is the part of Michigan that we're talking about, because Michigan is the mitten state.
Yeah, for the listener, Chris is holding his hand up to the camera, which is the classic. If you're not familiar, is the classic Michigander, person from Michigan thing to do. Is like when you ask where you're from, hold up your hand, because the state looks like a hand, so you point out.
Yes, that is so common that I run into a lot of people from out of state, and they always ask where I'm from, and we're talking, and so I got sick of like trying to pinpoint exactly where Southwest Michigan is, where I'm from, and so I got it tattooed on my hand. So I have a star on my hand.
Let's see it. Hold it up to the camera, Chris.
Right,
you're holding it up
right
properly.
There. There you go.
Chris
so
has
it's
got a star
right in there. Yep.
In Hudsonville, Michigan. Star on the hand.
Right.
That's amazing.
That's right.
So back to the Petoskey. If you hold your hand up, your thumbs to the right. The Petoskey stone rocks are exposed up in your fingertips. Not quite your fingertips, but your top knuckle there, basically.
That's right.
So, Chris, I'm going to skip ahead an image here. And again, we can, if you're listening on the podcast or if you're on YouTube and you want these images, we've got them on the app. You can go to our app in the visual podcast series. We've got these images displayed there too, just under the Planet Geo stuff there. So download first link in your show notes. But Chris, this is setting the scene. Like, what did the world look like? I love, and you're the best at this, at painting pictures that the rocks tell us. So go
about that. But so this is 375 to 360 million years ago, and this part of Michigan at the time was a warm, shallow sea. And that's pretty typical because the Devonian period is generally considered to be warmer than before that and after that. So this was a warm time. And so during this time then, sea level was higher all across the board for the most part. So
well, Chris, let's look at this image here a minute. You're exactly right. And we have to visualize, like, think about the continent. We've done episodes on hypsometry, or the hypsometric curve. Think about what happens if you flood the continents. Think about what happens if you raise sea level a kilometer, or let's say 500 meters. Most of the eastern part of North America, and actually all of the Canadian Shield, is very flat and very close to sea level within a couple hundred meters. So if you just raise it a couple hundred meters, you flood the entire part of the continent. And the only thing that's left sticking up is the high relief stuff. You know, once you get out to the Rockies or once you get out into the western United States, that's high relief. So this image,
and that's a really good.
Sorry, go ahead.
No, I was just going to say that's a really good point, because this is a part of the broader Michigan Basin. You know, Michigan Basin is like this downwarped, but it's like a circular syncline, or like a big broad salad bowl sitting right side up.
That's a good description.
That's the geology of Michigan. And so this is this like subsiding, this kind of sinking intracratonic basin that was sinking due to the sediment that, you know, it was like this ideal setting for a really warm, shallow sea.
Yeah, totally.
And the deposition that was happening then just allowed for more deposition because of all the weight of the sediment that was accumulating. And so,
and it's sitting, Chris, again, this is sitting on continents. So we're depositing, we often think of sediments going out into the ocean basin. This is sediments being deposited on the continent, you know, on a submerged part of the continental crust. And as you said, it's kind of subsiding as you put that weight, redistribute that weight around the continent, it sloughs down. We've talked about how you form basins before, so go back to an episode, I don't know, 6 months ago on the Michigan Basin and how you kind of can start to form these little basins. And there's little basins all over this part of North America. The Michigan Basin is one of them that started to deposit these rocks. We're also, Chris, nearer the equator, or near-ish to the equator, right? So it's a warm period. The Bahamas is kind of a good analogy. So picture the Bahamas.
Yes.
Not necessarily tectonically, but as far as like a surface environment, we've got this subsiding platform that's sort of shallow, warm, probably very beautiful if you ignored all the scary creatures going around.
The water's beautiful too, right? Then that's an important part of this, is that we kind of need this setting to be a sediment starved kind of situation, because that allows for this really clear sunlit waters that are good for reef development, which is essentially what coral is. This is a part of the reef family.
Okay.
A part of what Petoskey is. This organism that forms the Petoskey Stones is a part of that reef family.
Yeah. So you picture, you know, you get out in the Bahamas a little bit and you have this shallow setting. There's all sorts of life going on, coral reefs around. They're growing. As they grow, they build up that system, and there's some balance between sea level and where the creatures are happiest in there. And, you know, sediment is kind of coming off, and you think of like a carbonate mud, these sort of muddy, oozy carbonate sequences that are being deposited down, burying. You know, reef gets built up, it gets buried by, you know, carbonate kind of sloughing off, and then a new one pops up, and that's what's kind of going on here in this sequence of carbonates. And this is in a sequence of sediments that are exposed all throughout Michigan. We're zooming in on one particular unit here that is exposed, as you said, in those upper knuckles of your hand in Michigan.
Yeah, I want to have you take a step back, Jesse, because I don't want to be confused. We're talking about these like sediment starved water, and then you talked about this kind of muddy ocean bottom, which is not to be confused with muddy water, right? Just can you clarify that point a second before we go ahead and move on?
A lot of these rocks so it's a time period where we transition from, when you say sediment starved, you mean not a lot of mud
clay
being dumped
yes.
by the Mississippi River into the ocean basin nearby. It's clear water. There's not a lot of sediment, not a lot of sand grains or mud pieces, clay particles being dumped in by the river system. When I say clay mud or carbonate mud, I mean, chemical precipitate mud.
More like a jelly ooze, right? Kind of this silicious, or not silicious, this carbonaceous ooze.
Or actually kind of storm broken apart pieces of reef systems. So storm comes in and kind of breaks apart the stuff that's on the bottom and reworks it over time. And so that's kind of what we're talking about here. Okay, so we're on this muddy thing where there's a whole sequence of rocks that we're going to ignore for now the sequence of rocks. We're going to focus in on this Traverse group, which is
hold on. Is it really the Traverse group though, Jesse? Is it really the Traverse group?
It's a let's move forward in one image here. So this is a geological map. This is ignoring the till. All the till that's on covering Michigan. This is the bedrock map of Michigan. And all we've highlighted here is the Traverse group. And the way to think about sedimentary packages is we break them apart into different units. And one unit is a group. A group is a group of formations that all kind of share similarities. So the Traverse group will be kind of a limestone-dominated sequence with variations. There's always variations in here. And then we've put a star on here for the Gravel Point Formation, or one of the locations where the Gravel Point Formation is exposed at the surface, which means a potential source for Petoskey Stones. This is where one argument for one of the many places that Petoskey Stones could actually be coming from, which is a question that we'll touch on later. Like, where did these Petoskey Stones distributed all over Lake Michigan? Where'd they come from? It's an interesting problem. So anyway.
But Jesse, are we going to get some blowback from people that say it's not called the Traverse group, it's called the Alpina limestone, and
okay, yes, okay, that's a good question. Alpina, if you're holding it back to your hand, which way is right for me? Is this correct for you, the hand, or is it backwards? Is this right?
No, that's right. No, you're right. You're right. No.
This is right. Alpina's on.
No, that's not right. Flip it back.
This way's right. Okay, my camera's getting reversed in the thing. Anyway, if you look at your hand, the Alpina's on the thumb side. It's on the eastern side. The north, it's like your index finger, upper knuckle of your index finger. And there's a famous limestone quarry up there. And so the limestone there has been named the Alpina limestone. It is correlative. You can correlate that across to the western side of the state. And it ebbs and flows throughout this sequence, this purple Traverse group that is highlighted here in this map, in this image. You can kind of trace it discontinuously across, but if you go in different areas, they've seen different names. And this is like one of the problems in geology, actually. Chris, have you ever looked at a geologic map that is a big compilation map, and there's a really sharp straight line on the map separating units before? Like, you have one unit on one side and a straight north-south line and a different unit on the other side. Have you ever seen that in geologic maps?
No, I've not.
Well, up in northern Canada, this happens a lot because there'll be people who compile the geological map for the Slave Craton.
Oh, okay.
In one,
different regions.
In 1980, they mapped one quadrangle, and in 1995, they mapped the neighboring quadrangle, and they kind of have slightly different nomenclature on either side of that boundary line. And so, the compiler is like, I don't know which one to call it. It's clearly the same rock unit, but there's different descriptions, and, maps kind of have just... the people who do the maps kind of develop these different sort of mental models for it. So I think this happens frequently in geology. You kind of have to say, okay, the Traverse group, this limestone that we're interested in, which on the west side is the Gravel Point Formation. That's what people think as the source of Petoskey Stone fossils. That's probably, or almost certainly, correlated to the Alpina limestone, which I've been to. We did an undergrad field trip in this great invertebrate paleontology class. We went up to the Alpina limestone area and quarry and then the beaches and saw these carbonate reef systems. Probably the same time frame, if not the exact same layer. It's probably pretty damn close to the exact same layer.
It's nomenclature. It's more geography related than where you happen to be from in terms of what you prefer to call it, for sure.
Yeah, It's a human division. Absolutely. And Chris, as we know from your watermelon days, you're a lumper and not a splitter, right?
I'm a lumper. I'm world-class lumper, Jesse.
You are
don't you forget it. But real quick, before we move on to the reef ecosystem part of this talk, is if you look at this image, though, you can kind of see the structure of the basin that surrounds and defines Michigan here. You kind of see these concentric rings. And if we zoomed out more from this, you would see that it forms this bullseye pattern where the rocks crop up, the same rock types crop up all around the state. And
Chris,
they get progressively younger toward the center of it, which is what you get in a basin.
I was going to ask you that question. Okay, Drew, give me an analogy for that.
Come on, really?
I know. Well, quiz for you. Hold on. Back out and tell me the rule of a dome versus a basin, because domes have this same bullseye geological map expression. But dome versus basin, tell me the rule.
Well, imagine a bunch of sedimentary strata, stratigraphically spread way out, right? And then a piston, like a slug of magma, shoves the sedimentary rocks up. That's gonna accelerate weather and erosion there, and so you're gonna get old rocks exposed in the center of the dome, and the younger rocks are gonna be exposed on the edges. And that's switched around with the basin, because if you imagine a bunch of, let's say you have 5 meter sticks stacked up on top of each other. And the one on the bottom is the oldest in sedimentary rocks, and the one on the top is the youngest. And if you bend those up like a syncline, like a trough, okay, the bottom part, the oldest one, is going to show up then way out on the edge of where you bent the meter sticks. Yeah, and a basin is just a circular syncline. So it's that's the rule. Youngest in the center, oldest on the edges, and that's that defines Michigan. Like, you want to find the old rocks, go way to the UP, and that's where you're going to get into the very, very old Precambrian greenstone belt rocks and so on. Yep.
So Chris, another question for you. Do you still carry around a wooden yardstick in your class all day, every day?
Oh my gosh, I just broke one the other day. I didn't intend to. Yep. I use it all the time. Let me see. What was I talking about?
Okay. Well, how did you break it?
Oh, you know what I was doing? Okay, I was showing how subduction zones can generate tsunamis. So I took a meter stick and I had most of it on a lab table, but I had the last 12 to 20 centimeters sticking off the lab table, and I bent it down like what happens to the overriding plate in a subduction zone.
Gotcha. Yeah.
And I was showing how when you bend that down, it kind of curls down. It arches up the coastal area. It kind of bulges it up and can actually elevate it above sea level, right?
And so then the yardstick that's on the table, but just near the edge of the table, gets bowed up a little bit. Yeah,
bowed upward, right? And so then when it eventually breaks and gives way, the subducting slab dives down, and the overriding plate rebounds and snaps back up, and it makes a really loud noise, slapping noise on the lab table. And I bent it too far, and it just broke. And it scares me every time it happens.
So another question: what's your annual budget for yardsticks in your class?
I buy 30 at a time. Yep, I do. Yeah.
That's so good. Hilarious. Okay, well, that's a good analogy, a good deviation here. So we've painted the picture. Here's where the rocks are that we're looking at. We've got this ancient Devonian Bahamas style. Picture the Bahamas. That's what's going on. Here's where it's located now on the planet Earth. Get us from the Bahamas to the deposits now. Like, what happened in between there to get to these really cool Petoskey stone characteristics? What do we have to have happen, basically?
Okay, so Jesse, let's establish a little bit about this reef ecosystem going on here. I think it's important
fun to visualize. It's really fun to try and visualize these things, right?
Yeah, because when you look at the Petoskey stones themselves, you can't help but notice the honeycomb look to them, that kind of hexagon look to this. And so these were called, here's the sciencey term for it, but the Hexagonaria percarinata, which we call Petoskey stones. Okay, these
so Chris, that's the genus and species of this particular organism, right? That's the fossil organism that we're talking about here.
Yes. I mean, look, I think it's important to note that these are colonies, and these colonies are very, very diverse. We've seen these, Jesse, you and I personally, many different flavors of these kind of reef colonies, right? Think of in Glacier National Park, you have these stromatolites, which were very similar to this, much, much older, but similar because they formed these like cabbage head colonies, and they literally looked like leafy cabbage heads. And then you'd see these other ones that looked like stacked construction cones, and they're really like nearby. They're in close proximity with each other. So you had these different colonies growing at the same time. And this is just a type of colony that it's a reef organism, essentially.
Right. So Chris, the reef part, let me just touch on that and build on that a little bit, is what visual if you've never, gone snorkeling on a reef or something like that, had the benefit of doing something like that, what should you imagine? Finding Nemo. Imagine this Finding Nemo vision of the world where, there's a bunch of fish, they're living in there's all these creatures around, and then there's a pretty steep drop off down into deeper water somewhere. In the colony, the reef system, all these creatures building their homes out of minerals, calcium carbonate and aragonite, kind of build up this complex until it gets to really shallow water, and then you have this water that's trapped between the reef and the land surface, but it's they build up and get destroyed, and this kind of ebbs and flows. But the reef is a whole bunch of organisms, and we're focusing on one of the organisms in this particular ancient Devonian reef system. Chris, this image is a diorama of a rugose coral. It's not a colonial version. These are singular ones, but it kind of gives us an idea of what the coral organism might have looked like.
It does. I like this diagram, or image. The only thing that would make it look more real would be to have this kind of hexagonal top to it, which is what we see when we polish up a good sized Petoskey stone.
That's right. So, Chris, these are the species represented in this diorama is an isolated, a lone rugose coral. So they grow on their own. The ones that make Petoskey stones are a colonial fossil, which means that they grow together. These things grow up, and basically what you got to envision is they start small, and as the colony grows, you have more organisms, and they're six-sided. I'm going to skip ahead here. They're six-sided because or generally kind of they're trying to be six-sided mostly because that's the most efficient way to share sides, right?
They're sharing walls, right?
They're sharing walls
they're growing.
with each other, right?
Yeah, that's right.
So it's a big apartment building of corals. And as this colony grows, think of like a half moon on the ground. And as the colony grows, you get more organisms. They have to grow upward and outwards. And so the colonies, the little organisms only exist, the polyps exist right on the surface. And as the colony grows, they kind of have to build floors underneath of them. And as they get more organisms, it has to kind of expand outwards. And so all the creatures, all the polyps have to kind of move their apartments up a floor. They got to add another floor to their apartment, move to the outside so they can go grab some food from the water around it. And so what we end up doing is this colony gets bigger and bigger and bigger, more organisms get added to it, it grows upwards, and so it gets segmented. And so if we look, this is the really beautiful view of a Petoskey stone here. If you cut this in half, like cut a slice of this, you would see that these things get smaller. And if you look at that, cut it longitudinally, cut it in half, you'd see these segmented floors that look like floors, and that's actually the polyp kind of growing, and then it says, oh, I'm too deep, my walls are too high above my head, I need to move outwards a little bit. So it builds a floor, moves itself outward, and this happens as the colony gets bigger and bigger and bigger. So it's like
an upside down construction cone, I think.
Oh, that's
the way
a good way to describe
it.
Yeah. That's a really good way to describe it, Chris. Yeah. And I think it's almost as beautiful cut in the other direction. Like, this is the classic view of a Petoskey stone here, but it's almost as pretty cutting in this direction where you kind of see the floors or the segments in that I
have a question.
Stone.
What builds the floor, though? Is it algae that helps them secrete this kind of jelly-like calcareous ooze that makes the floor then?
Yeah, I know. You're referring to the corallites, like the individual individual apartments here. I don't know that, actually. I'm not sure what initiates that growth. That's a good question. Again, see above, we're not biologists.
Right. We're not.
We
can appreciate the biology here, but yeah, that's right.
Here we can. Here's one instance we can.
So, Jesse, how about we transition then into like this I think of this as like a 3-step process. We have sedimentation going on, we have diagenesis, and we have then fossilization happening.
You mean taking this live colony and turning it into the rock we see today?
Into the rock.
Okay. Yeah.
Yes,
right.
Absolutely.
Perfect.
So let's take each of these segments kind of briefly here in terms of, it's in this order. So like when the corals die, think about what happens to them. Well, they got buried. They got buried by more limestone. Right now, this is different. This was a transition from a reef kind of paleo setting into just simply more of a more typical limestone sedimentary rock deposit. Is that a fair assessment?
I think that's completely fair. And you just think of there's all sorts of reasons that a reef, an entire reef ecosystem, or just particular colonies could die, right? And then get buried by this mud, this limestone, this calcareous mud gets buried, and you can have whole reef systems that pass away and die for climate reasons or perturbation reasons. They get a big storm comes through and just floods this thing with a whole bunch of sediment. The whole reef system dies.
Muddy the waters and things change, right? And this is with. Go ahead. Well, I was just going to say, Jesse, when that sediment, when the coral dies, it's getting buried by this limestone. That's the reference to the traverse group that you talked about before.
Right.
So these really finely laminated traverse group right on top of the Petoskey Stones.
So, and Chris, this speaks to kind of the background, or actually the rock exposure itself. If you think about a reef system, and you think about the Bahamas, the reef is a relatively small part of the entire sedimentation system. That's true in a lot of places. There's a lot more basic limestone being laid down than there is reefs getting buried. And that's true back into the past too. Reef fossils they're not rare. They're all over the place, but they're not incredibly common. There's a lot more rock that is just, in my mind, a little bit of a boring limestone. Then there is Petoskey Stone part of this rock. Does that make sense?
Yes.
Yeah.
That's a totally fair thing, and you're not offending me by calling it more of just kind of this boring limestone. You're definitely offending some people, though. I guarantee you that. But
we're among friends here, so it's all good.
That's right. That's right. It's all tongue in cheek, everyone. It's all yeah. So all right. Well, this gets a little doctory, actually, professor. There, I just called you professor, but
thank you. Professor,
where we get into, so you have the sedimentation process, and then you have the diagenesis process, and diagenesis is this like techie word. I think I don't know. This is not really a intro level word. I wouldn't say. Would you? I don't use diagenesis in my classes. I just don't.
Yeah, I use it, but not. It's not on the need to know basis for sure.
Okay. Yeah, that's right. That's right.
Yeah.
Diagenesis is this kind of garbage can term that refers to the series of physical and chemical changes that occur or that happened to this system. And in this case, it refers to permineralization, recrystallization, and then lithification. So let's talk about each one of those, Jesse. Just a brief synopsis of what's involved in diagenesis.
Ooh. Diagenesis. This is taking a sediment and turning it into a sedimentary rock. You can also think of it as low-grade metamorphism. Those are two, I think, kind of interchangeable ways to think about it. So how do you take sand grains and make it a sandstone? You got to kind of bond the sand grains together in some way. You can cement those things together. You can precipitate quartz or something in there to precipitate them. You can put it under a little bit of heat, a little bit of pressure, and that also does the kind of bonding together.
Yeah.
And the same types of processes can happen to rocks. So diagenesis is that category of things. And you laid out three different ways to do it, or three overlapping ways to do it is a better way to describe it.
I think they're all involved in this, though, in terms of the preservation.
Exactly. So overlapping processes that they feed back into each other a lot.
They do, absolutely. Yeah. It's a positive feedback loop. But this permineralization is, I think of it a lot like how I think about petrification of wood.
Okay.
You know, you have these wood fibers that
analogy.
are soaking up this water that's rich in usually silica in terms of petrification processes. And then that silica gets precipitated inside the wood fibers, and it's turning this into rock. That's, I think, similar to what's happening here with the corals themselves. You have groundwater then that is kind of permeating its way through these skeletal structures, but the water is saturated with calcium carbonate. And so it's kind of precipitating calcite, essentially, limestone, within the pore spaces of what was left of now these dead corals. Does that make sense?
Okay.
So we're just adding, calcium carbonate as a filler inside of these kind of like horn-shaped corals.
Okay. Gotcha. Yeah, that's a good description. And so then we're going to, build on to that. And what's the next process, or the next overlapping process that can relate to this?
Well, recrystallization. This is a bit of a rabbit hole though, because most of the Petoskey stones were originally aragonite. And aragonite is a calcium carbonate. It's a polymorph of calcite. In other words, same chemical formula, but slightly different crystalline structure, right? And so what we had going on is the aragonite was stable when it was forming, but then later on, calcite's more stable. And so the calcite structure replaced the aragonite structure in this recrystallization process. The net effect of this recrystallization process of turning it back into calcite is that it made it tougher.
Yeah,
it made the Petoskey stones resilient.
More, yes, that's a good way to
adding
describe
survivability to, I guess, the rock itself.
Yeah, that recrystallization is essential, right? It's essential to the kind of fossilization part, and it helps explain the softness. You described very, very well how the sort of lapidary enthusiasts love this rock because it's so easy to polish. It's really easy to cut. I mean, a rock saw just churns through Petoskey stone like butter. It's amazing how quickly you can cut through a Petoskey stone. Like if you're cutting a granite on your rock saw and then you cut through Petoskey, it just rips through Petoskey stone because it's so soft, and because it's mostly made of these relatively soft minerals, calcite. There is a little bit of quartz recrystallization in here as well, and sort of replacement texture, but the calcite's very soft when it comes to a diamond impregnated steel blade, right? Or even just your sandpaper can polish this stuff really well. And then we end up getting to sort of lithification, right? And how does that play out in these rocks?
Well, it's lithification is burial and kind of further cementation. It's like you said, there's overlap between this and recrystallization. There's overlap between all three of these diagenetic processes, but lithification, it made it tougher yet again. This kind of compaction and further cementation, kind of gluing everything together one last time. This allowed it to endure. One of the final steps is we got to take this stuff and we got to move it. We got to move this due to glaciers. And that's not a non-violent process. It's not a passive process. And so that lithification helped it kind of gave it the last strength that it needed to make the final journey, I guess, if you will.
Yeah, to endure that. And that brings us really nicely, Chris, into like how do you get this stuff spread all over the state of Michigan? Let's go back to this let's go back to this map here a minute and go to image number 4 in our stack, which is showing this traverse group, which again is kind of, if you're not looking at the app, you're looking at the knuckles, the upper knuckles of your 4 fingers, not your thumb, but your 4 fingers. That's where we're kind of exposed there. And the gravel point formation is kind of your ring finger, upper knuckle of your ring finger on your left hand if you looking towards you. It's a really limited area of where we've seen a lot of these fossils in outcrop, and there's a bunch spread throughout here. But how do we get this stuff all over Michigan, all over Lake Michigan, the shores of Lake Michigan? It's a really, I think it's a cool question to ask with a very simple answer. And it's really glacial transport. Like we talked about when we were talking about pudding stones, Chris, in the Lorraine quartzite, in the Lorraine group pudding stone, in Lake Huron, when the glaciers scraped across here, they ripped up a ton of that stuff, deposited it in till all over Michigan, And then that stuff has just been continually reworked over time by all the sort of superficial processes for the last 10,000, 20,000 years that we've experienced on the surface.
It got exhumed.
It got exhumed. Yeah, that's exactly right. It got exhumed and
then it got transported.
Off,
it got plucked, and there you go.
Yeah,
there
exactly. And Chris, I've found Petoskey stones up in that especially that northwest part of the lower part of Michigan on the eastern side of Lake Michigan. There's a ton of sand dunes all the way down to Holland and all the way down south. Hundreds of feet high sandstone or sand dunes on the edge of Lake Michigan. And I've been up in this part of Michigan, up by the Petoskey Stone area, Grand Traverse Bay area, on big sand dunes. You're 300 feet above the surface of the water, and you're looking around. You find a rock buried in the sand dune. This is all glacial till that's been reworked, and some of the sand dunes are just windblown parts of that. And you pick it up, and it's an amazing Petoskey stone that's been weathered by the sand. Like, it's clearly been sand blown and sand. It's not polished. The pits, the inner parts get more weathered than the outer white rinds of it. And so I found these things, certainly no longer an outcrop, but in glacial till before. Have you found Petoskey stones in gravel pits before?
Oh, absolutely.
Chris?
For sure.
Okay.
Yes.
Yeah.
Yes.
So these are things that are reworked and dumped off in a gravel pit as the glacier meltwater is retreating, right? And it's just glacial erosion, picking up this stuff and dumping it in a big amalgam down further to the south and southwest.
Yeah. Yeah. It's interesting that, the Michigan Basin kind of protected this since Devonian until the Pleistocene glaciations took place, which is amazing. That's a long time, Jesse. We're talking 350 plus million years where it was just stable, because if it weren't stable, this rock would have been erased quite easily.
That's right.
Actually. And so the fact that it's still around was a little bit shocking to me, and it's a really cool piece of the story. It was protected, really, by the stuff all on top of it and by just the structure of the basin geology.
And Chris, these, it's an important point is that we talked about this basin geology. We talked about this back in previous episodes, and there are basins all over this part of North America that are similar age, have similar kind of depositional histories, and there are actually many very different but very related species of fossils to the one that has been designated the Petoskey stone, the state stone of Michigan. And there's at least 7 and more than that species that are quite related, that are actually, I'll be honest, I wouldn't be able to tell the difference between a lot of these, because it comes down to the number of segments and what the structure of these things looks like, and it comes a little bit to the lumper splitter argument of what are species and what are not different species. But there's a lot of different variations on this that are not necessarily the exact species that has been designated as the Petoskey stone, but look quite similar.
Yeah, they're in Canada, they're in England, Germany, even in Asia. So there were a lot of shallow seas that had this same kind of setting they could have been called Petoskey stones too, or they would have been called something else, obviously. But it's very similar to this species. Yes.
Yeah, that's right.
And
Chris,
sure.
This is just if you're from Michigan, this rock. If you're it's a very common collector's rock too, kind of like pudding stone, and maybe even more so than pudding stone, I'd say. You'll see it in rock shops all over the Midwest and all over North America, really. And I think part of the reason, Chris, that it's a spectacularly beautiful rock and that people really like it, it's how do I say this? It's like a little kid's dream rock, because it changes color. Doesn't change color, but the color change is so dramatic between wet and dry, right?
Yeah, that's right.
And this last photo is just a great one from the web that just shows, if you're wading in these beautiful clear waters of Lake Michigan, and you look at a dry Petoskey stone on land, you could easily walk across it. It's just a plain old, generally kind of drab gray rock, and you'd have to look kind of closely to see that there's these cool coral fossils in there. But if you get that thing wet, the white corallite, the white parts around the coral, each corallite, stand out like crazy, and the dark little eyes in the center stand out really well. And it's really stunning. You kind of look at it and you think, what is that rock? That's really cool. That's really pretty. And then you polish it and it gets even more beautiful. I just like this photo. It's a nice example of it just reminds me of walking along the shores of Lake Michigan in the summer, which you just can't beat that sometimes.
No, it's hard to beat. It absolutely is hard to beat,
right?
I mean, we're biased, everybody, but that's okay. It's our podcast, so we can be.
That's right. We're biased, but at least we're biased towards cool stuff. Great Rocks
I
is
hope
a cool story, right?
Yeah, it is a cool story. I mean, because think about this a second. This is a reef. It's a part of a reef system. And we're in the middle of the North American craton. That's not an easy thing, I think, for a lot of people to imagine. Wait a second, what? And then you look at other parts of the surrounding geology, where we have gypsum all over the place and these other evaporite deposits and limestone and dolostone. And we have in between the gypsum shale layers where there's shark teeth preserved in these shale deposits and coprolites, shark poop and things like this. And it's all a part of the story. It's a cool part of the story because it's so vastly different from what we see today. And I love that about geoscience is just contemplating things like that.
I think you're exactly right. And it just brings to mind that every rock tells a story, and the story is often a story of a very different world than we currently inhabit.
Yes.
And in a world where the continents, the flat-lying parts of continents are flooded, is a very different world than the one that we currently inhabit. And it has very different creatures on it, and it has very different life forms. And the rocks tell the story. And I love these instances, Chris, where we get beautiful rocks that tell a really interesting story. I'm used to studying really not beautiful rocks that tell an interesting story about the early Earth.
Oh, come on.
They're not pretty. They're not pretty. They're not as pretty as Petoskey Stones. So it's always like a really good thing when it's also a pretty stone that tells a pretty good story, right? And so we like to focus on those ones.
Yeah.
So,
yeah. Well, what do you say,
Chris,
Jess? Is that a wrap?
Yeah, I want to go look for some Petoskey Stones, man. We'll try and make a trip this summer. Go look at some Petoskey Stones. That'd be great. Hey, I think that's a wrap. You can follow us on all the social medias. We're at Planet Geocast. Send us an email, planetgeocast@gmail.com. We always appreciate getting those. If you're on the podcast app, first link in your show notes is a link to our CampGeo mobile app where you can get this podcast with all the images that go along with it. If you're on YouTube or Spotify, please leave a subscribe, leave a comment, give us a like and a rating, and we love to hear from you.
Cheers.
Peace.